In 2022, the James Webb Space Telescope began transmitting observations from the universe's earliest epochs, and within months, astronomers encountered a problem that existing cosmological models could not easily resolve. Galaxies appeared far earlier than predicted, carrying stellar masses and structural complexity that should have required far more time to form. Supermassive black holes, already billions of times the Sun's mass, were detected in regions corresponding to a universe only a few 100 million years old. These were not isolated anomalies. Independent survey teams, using different instruments and wavelength analyses, kept finding the same pattern. According to the prevailing ЛCDM model, early cosmic evolution should have been gradual, with small protogalaxies slowly assembling over time. Instead, Webb revealed an environment of rapid star formation, accelerated chemical enrichment, and unexpectedly, mature galactic structures. Researchers are still debating whether the explanation lies in unseen astrophysical processes, missing physics, or limitations within the standard cosmological framework itself. What James Webb was actually built to find. The James Webb Space Telescope is not a more powerful version of Hubble. That framing, repeated in nearly every piece of public communication surrounding its launch, obscures the more important point. Hubble and Webb were designed to answer fundamentally different questions using fundamentally different physics, and the distinction between them is the reason Webb's results have been as disruptive as they are. Hubble operates primarily in ultraviolet and visible light, with some sensitivity extending into the near-infrared. It was built to see what the universe looks like in the wavelengths human eyes are sensitive to, and it transformed astronomy by doing exactly that. The Hubble Deep Field images, produced by staring at a tiny patch of apparently empty sky for days at a time, revealed thousands of galaxies at distances corresponding to 1 to 3 billion years after the Big Bang. That was the practical limit. Beyond those distances, the light from early galaxies had been stretched by the expansion of the universe into infrared wavelengths that Hubble's detectors could not adequately receive. The James Webb Space Telescope was built specifically to see what Hubble could not. Its primary mirror spans 6.5 meters across, assembled from 18 hexagonal, gold-coated beryllium segments, each weighing roughly 20 kilograms. The collecting area is roughly 6 times that of Hubble's 2.4-meter mirror, and light-gathering scales with area rather than diameter. So the improvement in sensitivity is substantial. But the mirror size is secondary to the detector design. Webb's instruments are tuned to wavelengths from 0.6 micrometers, just at the red edge of human vision, out to 28 micrometers in the mid-infrared. This range was chosen for a specific physical reason. The light from the universe's first galaxies, emitted in ultraviolet and visible wavelengths billions of years ago, has been redshifted by the expansion of space into the infrared by the time it arrives at Earth. No amount of mirror area can compensate for detecting the wrong kind of light. Webb was designed to receive the right kind. The engineering consequences of building an infrared telescope are severe. Infrared detectors are sensitive to heat, including the heat of the telescope's own components. Any warm surface in the optical path produces thermal noise that drowns out the faint signals being sought. Webb's solution involved a 5-layer sunshield the size of a tennis court, made from a material called Captain coated in aluminum and silicon, deployed to block heat from the Sun, Earth, and Moon simultaneously. The shield keeps the telescope's instruments at roughly negative 233 degrees Celsius, cold enough that the detector's own thermal noise is suppressed below the level of the signals arriving from objects that formed 13 billion years ago. To maintain this thermal environment permanently, the telescope was positioned at Lagrange point 2, a gravitational balance point approximately 1.5 million kilometers from Earth in the direction away from the Sun. At this location, the telescope can maintain its shield orientation continuously without interruption from Earth's shadow or the geometry of a low orbit. The cost is permanence. Unlike Hubble, which orbits at roughly 550 kilometers and was visited by astronauts 5 times for repairs and upgrades, Webb is at a distance that makes any servicing mission practically impossible with current technology. Engineers at NASA, ESA, and CSA identified 344 individual mechanical steps required to unfold and deploy the telescope after launch, each representing a single point of failure. Any one of them going wrong would have ended the mission permanently at a distance no crew could reach. The telescope launched on December 25, 2021, aboard an Ariane 5 rocket from the Guiana Space Center in Kourou, French Guiana. The deployment sequence over the following month executed without a critical failure, mirror segments aligned to a precision measured in nanometers. Instruments cooled to their operating temperatures. By the summer of 2022, science operations were underway. The scientific community's first reaction to the commissioning images was not satisfaction that specifications had been met. It was something closer to alarm, because the faint red objects visible at the edges of those earliest exposures were not distributed the way the models said they should be, and they were not as faint as theory predicted they would be. The instrument was performing at or above its design specifications. The problem was with what the design specifications had been built to find, and what actually existed when the telescope looked for it. There is one further technical detail worth establishing before moving to what the telescope actually found, because it explains why the results arrived with the speed and confidence they did. Webb carries 4 primary science instruments. The near-infrared camera, called NER-CAM, serves as the primary imaging instrument, sensitive to wavelengths from 0.6 to 5 micrometers and capable of simultaneously observing 2 fields of view, each measuring 2.2 by 2.2 arc minutes. The near-infrared spectrograph, NIR-SPEC, can take simultaneous spectra of up to 100 objects in a single exposure using a micro-shutter assembly containing roughly 250,000 individually addressable shutters, each smaller than a human hair in width. This multi-object spectroscopic capability was the instrument most critical to the early Galaxy science programs, because it allowed researchers to obtain precise redshift measurements for hundreds of objects in a single pointing rather than one at a time. The mid-infrared instrument, MIRE, extends sensitivity to 28 micrometers and provides both imaging and spectroscopy at wavelengths relevant for dust-obscured star formation and the thermal emission of very cold objects. The near-infrared imager and slitless spectrograph, NIRIS, provides additional spectroscopic modes, including wide-field slitless spectroscopy useful for surveying large populations of objects simultaneously. The combination of these instruments operating in the infrared from a cold, stable platform far from Earth's thermal environment produced a capability that had no precedent in the history of observational astronomy. Webb did not merely extend what was possible by a measurable increment. It opened a wavelength range and a sensitivity regime that had been completely inaccessible to all previous space-based and ground-based facilities. The universe had been broadcasting in that range for 13.8 billion years. As of mid-2022, humanity finally had a receiver tuned to the right frequency. What came through was not what the theoretical models had been predicting. The first images that made physicists go quiet. The first science image from the James Webb Space Telescope was released publicly on July 11, 2022. The target was a galaxy cluster designated SMACS 073, located approximately 5.12 billion light-years from Earth. The cluster itself was not the primary subject of scientific interest. It was a tool. A galaxy cluster concentrates so much mass in such a compact region that it warps space-time in its vicinity, bending the paths of light rays passing around it. This effect, called gravitational lensing, acts as a natural telescope magnifying and distorting the light from objects far more distant than the cluster itself that would otherwise be too faint to detect. The choice of SMACS 0723 was deliberate and methodical. The same field had been observed by Hubble, providing a direct calibration baseline. Every galaxy Hubble had seen there would serve as confirmation that Webb was working correctly, and everything beyond Hubble's detection limit would constitute new territory. The comparison that emerged within hours of the image's release was striking. Objects that Hubble had required 11 days of cumulative exposure, time to capture as faint, unresolved smudges, appeared in Webb's image with visible internal structure. Colour gradients indicating stellar populations of different ages, bright cores, extended halos, and in some cases features consistent with spiral arms. Webb had obtained comparable depth in a small fraction of Hubble's integration time, with sensitivity still substantially above what Hubble could have achieved even with extended observation. Within the arcs and smears of gravitationally lensed light in that first image were objects whose redshifts, estimated from their colours alone at that early stage, placed them at epochs when the universe was less than 1 billion years old. The scientific community's response was not uniform celebration. Several researchers, posting on public forums and preprint servers within hours, noted that some of the faintest, reddest objects in the image appeared brighter than theoretical predictions for galaxies at those distances expected them to be. The models allowed for some variation, but the trend was in an unexpected direction. The objects were not at the faint end of the predicted distribution. Some of them were at the bright end, or beyond it. The SMACS 0723 image was a commissioning demonstration, not a dedicated science program. The programs specifically designed to probe the earliest universe had not yet begun their pointed observations. What the commissioning data contained was a preview, a suggestion of a discrepancy that the dedicated surveys would either confirm or explain away. The researchers who noticed it were careful in their public statements. Confirmation from multiple independent programs using rigorous photometric and spectroscopic methods was necessary before any conclusion could be drawn. What they said privately among themselves was more direct. The first image looked wrong in a specific way, and it looked wrong in the direction the data would continue to point for the following 3 years. The program designed to go furthest into that territory was already being executed in parallel. The JWST Advanced Deep Extragalactic Survey, known as JADES, had been planned before launch as the most ambitious systematic study of early galaxies ever attempted. It targeted 2 fields that Hubble had stared at for weeks, the Goods North and Goods South fields, and it was equipped with a capability Hubble lacked for objects at these distances: the near-infrared spectrograph, an instrument capable of taking simultaneous spectra of hundreds of objects in a single exposure. Spectra provide precise redshifts derived from the specific wavelengths of known atomic emission lines, shifted by known amounts, confirming beyond ambiguity when in cosmic history a given object exists. They also carry information about chemical composition, star formation rate, and the presence or absence of an actively accreting black hole. The SMACS image had shown something was there. JADES was built to read what it said. The JADES program was led by Daniel Eisenstein at the Harvard and Smithsonian Center for Astrophysics and brought together researchers from multiple institutions across Europe and North America. Its design represented a convergence of everything the community had learned from Hubble's deepest programs about how to maximize information extracted from limited observing time. The Goods fields were selected because they had the deepest existing multi-wavelength data from every major observatory that had operated since the 1990s, X-ray coverage from Chandra, ultraviolet from Galaxies, optical from Hubble, infrared from Spitzer, radio from the VLA. Every galaxy JADES detected would have ancillary data from a dozen instruments across a dozen wavelength ranges, providing a complete physical characterization impossible from Webb's data alone. The scientific infrastructure surrounding those two patches of sky, built over 25 years by the community, was as important as the new telescope itself in making the results interpretable. Galaxies that should not exist yet. The first major spectroscopic results from JADES were published in January 2023 in the journal Nature Astronomy. A team led by Emma Curtis-Lake at the University of Hertfordshire reported spectroscopic confirmation of 4 galaxies at redshifts between 10.3 and 13.2, corresponding to a period when the universe was between 300 and 450 million years old. These were not photometric estimates derived from colour alone. They were direct measurements of specific emission lines shifted by specific amounts, constituting unambiguous confirmation that these objects existed at those distances and at those epochs. At the time of publication, they were the most distant spectroscopically confirmed galaxies ever recorded. That distinction matters not just as a record, but as a methodological benchmark. Every previous candidate for a high redshift galaxy had carried some probability of being a contaminant, a closer object whose colours mimic the signature of extreme distance, or an active galactic nucleus whose light was being misclassified. Spectroscopic confirmation eliminates those alternatives. The galaxies Curtis-Lake's team reported were definitively there, definitively at those distances, definitively old. The problem was their brightness. Under the lambda cold dark matter model, the framework that had organised cosmological research since the late 1980s, galaxies at redshifts above 10 should be rare, small and faint. The model describes structure formation as hierarchical and gradual. Dark matter, the invisible gravitationally dominant substance comprising roughly 27% of the universe's total energy content, collapsed first into small halos, regions of slightly above average density that gravity amplified over hundreds of millions of years. Gas fell into those halos, cooled, fragmented, and began forming stars. Over time, small halos merged into larger ones, and small galaxies merged into larger galaxies, and the universe built its structures from the bottom up, slowly, over billions of years. At redshifts above 10, the universe is less than 500 million years old. The hierarchical model allows for the existence of galaxies at those epochs, but they should be in early stages of assembly. Relatively low in total stellar mass, irregularly shaped, with star formation rates that reflect the limited time available for gas to have cooled and collapsed. The galaxies in the JADES data were not matching those expectations. Several of them appeared to contain more stars, more total stellar mass than the models allowed for at those distances. They were not faint smudges at the theoretically expected lower boundary of detection. They were objects with substantial stellar populations that implied a head start of unclear origin. Stephen Finkelstein at the University of Texas at Austin, leading the Cosmic Evolution Early Release Science Survey, reported a statistical surplus that made the problem concrete. Luminous galaxies at redshifts above 10 appeared in the survey data at a rate roughly 10 times higher than the standard model predicted. This was not a marginal discrepancy attributable to measurement error or sample variance. It was an order of magnitude excess sustained across multiple independent survey fields using multiple independent methods. Caitlin Casey at the University of California, Santa Barbara, co-leading the Cosmos Web Survey, one of the widest field programs undertaken with the telescope, addressed the situation directly. The survey was ultimately cataloguing roughly 800,000 galaxies spanning 98% of cosmic history, and the data arriving from its earliest epochs were consistently at odds with what the models predicted should be there. Casey observed publicly what many researchers were saying among themselves. Since the telescope turned on, astronomers had been wondering whether the data sets were breaking the cosmological model. The conservative responses came quickly, Perhaps stellar mass estimates were systematically inflated because the infrared light from actively accreting black holes was being mistaken for starlight. Perhaps the early universe experienced brief, intense episodes of star formation that made galaxies appear more massive than their time-average histories would imply. Both explanations were technically possible. Neither had independent support. Both were being proposed specifically because the data without them contradicted the model. The difficulty with conservative interpretations of this kind is not that they are implausible in isolation. It is that they require the early universe to operate in ways that are themselves without established physical mechanisms. Concentrated bursts of star formation at the required intensity, producing stellar masses comparable to the present-day Milky Way in a few 100 million years, had no identified driver. And explaining away the black hole contamination problem introduced a separate and equally serious problem about where those black holes came from and how they grew so large, so fast. The statistical robustness of the discrepancy also resisted the most common methodological objections. Early high redshift galaxy samples from Hubble were small, drawn from tiny areas of sky, and susceptible to the statistical fluctuations that affect any small sample drawn from an inhomogeneous distribution. A handful of anomalously bright or massive galaxies in a sample of dozens could reflect cosmic variance rather than a genuine systematic departure from the model. Webb survey programs were designed explicitly to address this objection. The Cosmos Webb survey covered an area of roughly 0.54 square degrees, large enough to statistically average over the structures that produce cosmic variance at the relevant scales. The JADES program targeted two independent fields separated widely enough that their overlap in cosmic volume is minimal. Finkelstein's CERS survey used a separate pointing in the extended Groth strip field. The surplus of luminous early galaxies appeared in all of them independently. Cosmic variance cannot explain a systematic excess that shows up consistently across programs targeting different regions of the sky using different observing strategies. The star formation efficiency that breaks the model. In February 2023, a paper published in Nature forced the galaxy formation crisis into its most specific and most uncomfortable form. Ivo Laber at Swinburne University of Technology in Melbourne led a team that analysed data from the Cosmic Evolution Early Release Science Survey and identified 6 galaxies formed within the first 500 to 700 million years after the Big Bang. Each was estimated to contain between 10 billion and 100 billion solar masses in stars. The Milky Way, a large spiral galaxy by present-day standards, contains roughly 60 billion solar masses in stars, accumulated over more than 13 billion years of cosmic history. These 6 objects, formed when the universe was less than 5% of its current age, were comparable to or exceeding the stellar mass of one of the largest galaxies in our local neighbourhood. The mass estimates themselves were derived from photometric measurements of the galaxy's infrared brightness, combined with spectral energy distribution modelling to separate stellar light from other contributions. The methodology had been developed and refined over decades of galaxy survey science. It was not new or untested. The results it produced, applied to the Webb data, were outside anything previously observed or previously predicted at those epochs. The physical constraint that makes these masses problematic is not a matter of theoretical preference. It is a matter of what is possible, given how much gas existed in the early universe and how fast that gas can be converted into stars. The process of star formation is self-limiting. When young massive stars ignite, they blast their surroundings with ultraviolet radiation, ionize the local gas, drive winds that expel material from star-forming regions, and collectively suppress further star formation in their vicinity. This feedback mechanism, observed in detail in star-forming regions throughout the local universe and confirmed in simulations at every scale, imposes an effective ceiling on how efficiently a galaxy can convert its available gas into stars. Across cosmic history, the measured star formation efficiency, the fraction of available baryonic gas that ends up in stars over a galaxy's lifetime, typically falls between 5 and 10%. To assemble 10 billion to 100 billion solar masses in stars within 500 million years, starting from the conditions that existed after the Big Bang, these galaxies would need to have operated at efficiencies approaching 100%. Every atom of available gas converted into a star, without interruption, from the first moment structure began to form, with no feedback suppression, no gas expulsion, no pauses. Not merely higher efficiency than observed in the nearby universe, physically impossible efficiency under the known mechanisms governing star formation at any epoch. Mike Boylan Colchin at the University of Texas at Austin, who had spent years developing theoretical predictions for early galaxy populations, stated the implications in a companion paper published in Nature Astronomy the same year. If the mass estimates were correct, the observations placed the standard model under severe tension. The phrasing is precise scientific language. In cosmology, severe tension is not an expression of mild concern. It is an acknowledgement that two things cannot simultaneously be true, and one of them needs to be discarded or fundamentally revised. Erica Nelson at the University of Colorado Boulder described the objects as absolutely wild, noting that they implied either an early universe operating under conditions of chaotic efficiency no model had assumed, or a universe in which the physics of star formation itself operated differently at early times under rules not yet identified. The objects informally acquired the label the universe breakers. The label proved accurate, not as hyperbole, but as description. Subsequent spectroscopic follow-up in 2024 introduced partial qualifications. A portion of the apparent stellar mass in some candidates turned out to originate from actively accreting black holes rather than stars, meaning some mass estimates had been somewhat inflated by black hole light contaminating the stellar signal. Guo Sun at Northwestern University and collaborators proposed that unusually intense star formation episodes could explain a fraction of the excess. These corrections reduced the magnitude of the crisis without resolving it. Even after the most aggressive downward revisions, the population of massive galaxies at redshifts above 10 remained roughly 10 times larger than standard predictions. The universe breakers were still breaking things. They were just breaking slightly fewer things than initially feared, which is not the same as breaking nothing. Black holes older than they are allowed to be. Supermassive black holes, the kind found at the centers of large galaxies with masses ranging from millions to billions of solar masses, are not exotic rarities in the present-day universe. The Milky Way hosts one at its center, Sagittarius A star, with a mass of approximately 4 million solar masses. Observations of nearby galaxies across a range of types and sizes have established that essentially every large galaxy harbors a central supermassive black hole, and that the black hole's mass correlates tightly with the properties of its host galaxy's central stellar bulge. The relationship is so consistent that it appears to reflect a fundamental coupling between the growth of black holes and the growth of the galaxies surrounding them. The chronological problem the James Webb Space Telescope introduced does not concern the existence of these objects in the present-day universe. It concerns when they got there. Growing a supermassive black hole from a stellar seed, the compact remnant left behind when a massive star exhausts its fuel and collapses, requires time. A stellar mass black hole produced by the death of a star 20 times the mass of the Sun begins with a mass of perhaps several solar masses. Growing from there to 1 million or 1 billion solar masses through the accretion of surrounding material requires sustained feeding at the maximum rate physics allows. That maximum rate has a name, the Eddington limit. It describes the balance between the outward radiation pressure produced by the energy released as in falling gas heats up, and the inward gravitational force pulling that gas toward the black hole. When a black hole accretes at the Eddington rate, radiation pressure equals gravitational attraction, and the luminosity is at its theoretical maximum for that mass. Sustained Eddington limited accretion, growing exponentially from a stellar seed, produces a doubling time of roughly 45 million years. To reach a mass of 1 billion solar masses, starting from a stellar seed of 10 solar masses, requires continuous Eddington limited accretion for approximately 800 million years, under ideal conditions, without interruption. The telescope was finding black holes earlier than that. Roberto Maiolino at Cambridge University and collaborators published results in Nature in 2024, confirming the presence of a black hole at the center of a galaxy called GNZ11, situated at a redshift of 10.6, corresponding to roughly 430 million years after the Big Bang. The black hole's mass was estimated at 1.6 million solar masses, accreting at approximately 1 solar mass of material every 5 years. Separate detections, combining James Webb data with observations from the Tundra X-ray Observatory, identified black holes carrying between 10 million and 100 million solar masses at epochs corresponding to roughly 450 million years after the Big Bang. The mass of the GNZ11 black hole is not itself impossible by simple calculation. 1 million solar masses is achievable under Eddington limited growth from a stellar seed in the available time, if accretion began immediately and proceeded without interruption. The difficulty is the broader population context. GNZ11 is not an isolated anomaly. It is one of many objects at comparable epochs, showing comparable characteristics. A universe in which black holes at these distances routinely contain millions of solar masses requires that those black holes routinely began accreting immediately after the first stars formed, all of them, without the pauses and disruptions that both observation and simulation indicate should interrupt the process. The statistics of a single lucky object are manageable. The statistics of a population are not. The population problem has a specific quantitative expression. Black hole growth under the Eddington limit follows an exponential function of time. The doubling time, the period over which a black hole doubles its mass under sustained maximum accretion, is approximately 45 million years. Starting from a stellar seed of 10 solar masses and accreting continuously at the Eddington limit for 400 million years, produces a final mass of roughly 10 million solar masses. That calculation sets an upper bound. It assumes maximum possible accretion rate, no episodes of quiescence, no feedback-driven suppression of the gas supply, and no disruptions from the merger events and gravitational encounters that are characteristic of the early universe's violent dynamics. In practice, observed black holes in the local universe show evidence of episodic accretion punctuated by quiescent periods. If the early universe black holes accreted episodically rather than continuously, which is both physically expected and observationally supported by the range of luminosity seen in early active galactic nuclei, then the mass achievable in 400 million years drops substantially below the theoretical maximum. Yet the masses observed are at or near that maximum across a population of objects, not just in 1 or 2 exceptional cases. That is the core of the chronological problem, and the James Webb Space Telescope made it precise and statistically robust, where previous observations had only hinted at it. The deeper crisis arrived in the form of a catalogue. Jorrit Matthey at the Institute of Science and Technology Austria and colleagues characterized a class of objects systematically in 2024 that had been appearing in survey data since the telescope's first science year. They appeared compact, red, with spectral energy distribution shaped roughly like the letter V when plotted across wavelength. Their central black holes range from 1 million to 100 million solar masses. They became known informally as the little red dots, a name that understated the severity of the problem they represented. The little red dots, nobody can explain. In the present-day universe, the mass of a galaxy's central black hole typically represents approximately 0.1% of the total stellar mass of the surrounding galaxy. This ratio, known as the black hole to bulge mass ratio, has been measured across hundreds of galaxies spanning a wide range of types and masses, and it holds with remarkable consistency. It is one of the most robust empirical relationships in extragalactic astronomy, and its consistency across different galaxy populations suggests it reflects something fundamental about the coupled growth of black holes and their host galaxies. In the little red dots, the ratio ran to 30% or higher. The black hole accounted for 30% or more of the total stellar mass of the system it occupied. That is a factor of 300 above the locally observed relationship, not a mild deviation, but a categorical departure from everything the local universe had established as normal. These objects did not merely challenge a parameter of the standard model, they challenged the framework that produced the black hole to bulge mass ratio in the first place. The idea that black hole growth and galaxy growth are regulated by the same feedback processes and proceed in step with each other over cosmic time. Matthey's team catalogued 341 of these objects at redshifts between 4 and 8, corresponding to a period roughly 600 million to 1.3 billion years after the Big Bang. That redshift range is not the earliest epoch Webb probes, but it is still a period when the universe was less than 5% of its current age. And 341 confirmed objects is not a statistical fluctuation. The little red dots appeared at a frequency 10 to 100 times higher than any model had predicted. Their central black holes outweighed their own galaxies by ratios observed nowhere in the local universe, and the models had no mechanism to produce them in anything approaching the observed numbers. 3 explanations were proposed, each carrying problems. The first invoked direct collapse black holes. Under specific conditions in the early universe, a sufficiently massive cloud of primordial gas might bypass the stellar phase entirely and collapse directly into a black hole carrying 10,000 to 100,000 solar masses from the outset. This would give early black holes a head start over stellar remnants, allowing them to reach observed masses more quickly under Eddington limited growth. The conditions required for direct collapse are physically plausible. A cloud bathed in intense ultraviolet radiation, suppressing the molecular hydrogen cooling that would ordinarily allow fragmentation into stars, in a region where gas temperatures remain above the threshold for atomic hydrogen cooling. Such conditions existed in the early universe. Whether they existed with sufficient frequency to produce 341 catalogued objects, and whether the mass function of the resulting black holes matches what the little red dots show, remained unresolved. The second explanation required super-Eddington accretion, growth rates exceeding the theoretical maximum by factors of several, sustained over hundreds of millions of years. Super-Eddington accretion is not prohibited by physics. Simulations demonstrate it can occur briefly under specific geometric configurations of surrounding gas. But sustained super-Eddington growth across the timescales needed to produce the little red dot population would require conditions that remain persistently favourable for longer than any simulated episode. And the radiation produced by a black hole accreting at 10 to 20 times the Eddington rate would be energetic enough to heat and expel the surrounding gas, shutting off the very fuel supply sustaining the growth. The little red dots showed evidence of concurrent star formation in their host galaxies, meaning the black hole's radiation was not clearing the galaxy of gas while accreting at extreme rates. How both processes coexisted without one suppressing the other had no identified mechanism. The third possibility had fewer advocates, but was harder to dismiss entirely. Primordial black holes, objects that form not from stellar collapse, but directly from density fluctuations in the very first seconds after the Big Bang, had been theorized for decades as a possible contributor to dark matter. if primordial black holes formed in sufficient numbers and with sufficient mass during inflation or the subsequent radiation-dominated era, they would provide seeds far more massive than any stellar remnant, bypassing the chronological bottleneck that made stellar seed growth so difficult to reconcile with early high-mass detections. The challenge was that no direct observational evidence for primordial black holes had been established, and the parameter space required to produce them in numbers consistent with the little red dot catalogue was not well constrained by existing cosmological data. Matthey stated directly that his team was struggling to interpret the light they were observing from these objects. 341 catalogued objects, and the theorists examining them could not agree on what any of them were. That is not a provisional uncertainty pending a minor adjustment. That is an acknowledgement that the objects existed in a category without a clean precedent in the local universe, governed by physics the field had not yet identified. Oxygen in a galaxy, born 290 million years after the Big Bang. On May 30th, 2024, a collaboration of researchers including Stefano Carniani at the Scuola Normale Superiore in Pisa, Brant Robertson at the University of California, Santa Cruz, Kevin Hainline at the University of Arizona, and Ben Johnson at the Center for Astrophysics at Harvard and Smithsonian announced the spectroscopic confirmation of the most distant galaxy ever directly measured. The object, designated JADES GS-Z140 in the survey catalogue, carried a confirmed redshift of 14.32. That number translates to a specific moment in cosmic history, 290 million years after the Big Bang. The photons recorded by the telescope left this galaxy when the universe was approximately 2% of its current age, predating the formation of our solar system by more than 9 billion years. The object was not a faint detection at the edge of the instrument's sensitivity. It measured over 1/600 light-years across and contained hundreds of millions of solar masses in stars. Robertson noted at the time that the team could have detected this galaxy even if it were 10 times fainter than it appeared, suggesting that similar or larger objects awaited detection at even earlier epochs. The confirmation was remarkable as a record-breaking distance measurement alone. What followed made it something more consequential. In March 2025, combined observations from the James Webb Space Telescope and the Atacama Large Millimeter Array, the radio telescope network operated from the high-altitude plateau in Chile, detected a specific chemical signature in the spectrum of JADES GS-Z140 oxygen. The significance of this detection is not subtle and cannot be explained away by measurement uncertainty or instrumental artifact. Oxygen is the third most abundant element in the universe overall, but it is not primordial. The Big Bang nucleosynthesis that occurred in the first 3 minutes of the universe's existence produced hydrogen, helium, and trace amounts of lithium. Every atom of oxygen anywhere in the universe was forged inside a star, in the nuclear furnace of its core, and released into the surrounding environment when that star died, either by shedding its outer layers at the end of its life, or by exploding as a supernova. For oxygen to be present in a galaxy, that galaxy must have already hosted generations of stars that lived complete stellar lifespans and died. The minimum timeline this requires is constrained by stellar physics. Massive stars, the ones that explode as core collapse supernovae and distribute their nuclear products most efficiently into the surrounding gas, live for a few million to a few tens of millions of years. The oxygen enrichment visible in JADES GS-Z140 required at minimum one generation of massive stars to have formed, burned through their fuel, and exploded as supernovae before the galaxy's observed epoch of 290 million years after the Big Bang. Under the models that existed before this telescope, the year 290 million after the Big Bang was barely beyond the expected onset of star formation itself. The very first stars were theorized to begin forming somewhere around 100 to 200 million years after the Big Bang, in the dark matter halos that gravity had begun to assemble from the density fluctuations imprinted at inflation. That left at most 90 to 190 million years for an entire sequence. First-generation stars form, live their full lives, explode as supernovae, enrich the surrounding gas, allow a second generation to form from that enriched gas, and produce a galaxy massive enough to be detectable across 13.4 billion light-years of cosmic expansion. Massive stars live for millions of years, not hundreds of millions. The timeline is physically compressible, but it required that star formation began essentially at the earliest possible moment, proceeded at maximum efficiency without any of the delays and suppressions that characterize star formation in the local universe, and that the enriched gas recycled into new stars fast enough to build the observed system in the available window. Robertson described the finding as completely unanticipated. The word is accurate as a description of what the standard model had anticipated for that epoch and what the data showed instead. The oxygen detection also carries implications that extend beyond the specific case of JADES GS-Z140. The presence of oxygen enrichment at 290 million years after the Big Bang means that the process of stellar nucleosynthesis, the forging of heavy elements inside stars, and their distribution into the surrounding interstellar medium through stellar winds and supernova explosions, was already well underway within what the models described as barely the opening phase of star formation. The universe was not just forming its first stars at that epoch. It had already completed at least one full cycle of stellar birth and death, with the products of that cycle fully incorporated into new gas clouds that had themselves collapsed and formed the next generation. This is the chemical clock in action, and it was ticking far faster than the models had set it. Oxygen is a tracer element in this context because its production pathway is well understood. It forms primarily in the cores of massive stars through the fusion of carbon and neon during the later stages of stellar evolution, and it is distributed efficiently into the surrounding environment by core collapse supernova. A galaxy's oxygen abundance, measured through the strength of specific spectral emission lines called forbidden lines of ionized oxygen, provides a direct readout of how much stellar processing the galaxy's gas has undergone. High oxygen abundance means many generations of massive stars have already lived and died. At redshift 1432, the oxygen abundance in JADES GS-Z140 was not at the primordial floor. It was measurably above it by an amount requiring a history of star formation and chemical enrichment that the standard model had not placed at that epoch. The telescope was reading a chemical biography of a galaxy that the model had not yet finished writing. The Hubble tension gets worse with better data. The measurement of how fast the universe is currently expanding, expressed as the Hubble constant in units of kilometers per second per megaparsec, has been one of the central preoccupations of observational cosmology for nearly a century. Edwin Hubble's original measurement in 1929 established that distant galaxies recede from us at velocities proportional to their distances, constituting the first empirical confirmation that the universe is expanding. The constant bearing his name quantifies the rate of that expansion, and pinning it down with precision has driven some of the most ambitious observational programs in the history of the field. By the 2010s, two methods for measuring the Hubble constant had been developed to high precision, and they disagreed. The first method uses the early universe as a reference. The cosmic microwave background radiation, the thermal afterglow of the hot, dense plasma that filled the universe before neutral atoms could form, carries within its temperature fluctuation pattern a precise record of the conditions at recombination, roughly 380,000 years after the Big Bang. The Planck satellite's measurements of that pattern, published with the highest precision in 2020, produced a Hubble constant of 67.36 kilometers per second per megaparsec, with an uncertainty of plus or minus 0.54. The second method uses direct measurement of distances and recession velocities in the local universe. The approach proceeds in a calibrated chain. Parallax measurements of nearby stars establish a geometric baseline, which calibrates Cepheid variable stars in nearby galaxies, which calibrate type IR supernovae bright enough to be seen across billions of light years. Adam Rees at Johns Hopkins University, leading the SH0ES collaboration, refined this chain over more than a decade. By 2022, his team's measurement stood at 73.17 kilometers per second per megaparsec, with an uncertainty of plus or minus 0.86. The two values differ by approximately 6 kilometers per second per megaparsec. Expressed as a statistical significance using the combined uncertainties, the discrepancy stands at 5 to 6 sigma. In particle physics, 5 sigma is the established threshold for claiming a confirmed discovery. In cosmology, a 5 sigma disagreement between two methods measuring the same fundamental constant of nature is a crisis, not a source of mild professional disagreement. Either one method contains a systematic error that has survived years of scrutiny by independent teams, or both methods are correctly measuring quantities that genuinely differ because the universe does not behave the way the model connecting them assumes. The most plausible resolution, for years, was instrumental. The JADES distance ladder used the Hubble Space Telescope for its critical Cepheid calibrations, and any systematic error in Hubble's photometry at the distances involved could potentially bias the result. This was not an implausible concern. Hubble's optics are subject to crowding effects in dense stellar fields, detector nonlinearities, and calibration uncertainties that compound across the rungs of the distance ladder. If the photometry was systematically off by even a small fraction, the final Hubble constant value could be pulled upward from its true value. The James Webb Space Telescope was applied to exactly this test. With its superior resolution and infrared sensitivity, it could observe the same Cepheid stars in the same galaxies as the SH0ES program with higher precision and in wavelength ranges less affected by dust extinction. Rees's team published their Webb calibration results in 2023. The conclusion was unambiguous. The James Webb Space Telescope confirmed the Hubble Space Telescope's Cepheid measurements with high precision. The local Hubble constant measured from the calibrated distance ladder was 72.6 kilometers per second per megaparsec, matching the Hubble Space Telescope's value of 72.8 within the measurement uncertainties. Instrumental error in the distance ladder had been the most plausible single explanation for the tension. The most capable telescope ever built ruled it out. What remained after that ruling out was stated directly by members of the SH0ES team. A real and unresolved discrepancy between two precise measurements of the same quantity, made using entirely different physical phenomena, pointing to something the standard model does not contain. Either the early universe model is incomplete, or the local universe measurement is incomplete, or the physics connecting them has an error that neither dataset has yet identified. Wendy Friedman at the University of Chicago, leading an independent team using alternative distance indicators, including the tip of the red giant branch method and carbon-rich variable stars, found that 2 of her 3 independent approaches converged on the Planck value rather than the SH0ES value. Her interpretation was that a systematic error persisted in one of the approaches. Rees maintained that his method had been scrutinized by multiple independent groups over more than a decade and that the discrepancy was real. The field has no consensus. What it has, confirmed by the most precise telescope ever constructed, is a genuine unresolved crisis at the foundation of its quantitative framework. The cosmic web is more structured than it should be. The distribution of matter in the universe is not uniform. At the scales of individual galaxies and galaxy groups, this is obvious. Some regions of space contain dense stellar populations, others appear nearly empty. But the non-uniformity extends to much larger scales, organised into a coherent architecture that spans hundreds of millions of light-years, the cosmic web. The cosmic web emerged from the same quantum fluctuations that seeded galaxy formation, amplified over hundreds of millions of years by gravity into a three-dimensional network of filaments, sheets, and nodes surrounding vast, nearly empty voids. Matter fell preferentially along the channels defined by the dark matter distribution, accumulating where those channels intersected into dense galaxy clusters and progressively evacuating the regions between them. The result, visible in large-scale galaxy surveys spanning hundreds of millions of light-years, resembles in two-dimensional projections a foam or sponge, interconnected bright strands with luminous nodes at their junctions, and dark spaces of varying size between them. The existence of this structure was predicted by the lambda cold dark matter model before it was observed in detail. Galaxy surveys from the 1980s onward confirmed the broad architecture: filaments, walls, clusters, and voids, arranged in a pattern broadly consistent with what simulations of dark matter-dominated structure formation produced. The model's success in predicting the cosmic web's general character was one of its most significant observational validations. What the James Webb Space Telescope added was temporal reach. Previous surveys had mapped the cosmic web in detail at relatively nearby distances, corresponding to epochs when the universe was several billion years old. Webb's infrared sensitivity extended that mapping backward in time, tracing the large-scale structure at epochs corresponding to the universe's first 2 billion years, and measuring the positions and velocities of individual galaxies within those early filaments, with spectroscopic precision rather than photometric estimation. What the data showed was that the cosmic web's basic architecture was in place earlier than the models predicted. Substantial galaxy clusters connected by defined filaments appeared at epochs when, according to the standard model, structure formation should still have been in its early assembly phases. The filaments themselves carried galaxy populations denser and more massive than simulations produced at those redshifts. The universe had organised itself into coherent, large-scale structure faster than the model allowed for. The implications extend beyond the early universe. R. Brent Tully, at the University of Hawaii, whose work on cosmic velocity flows has mapped the gravitational landscape of the local universe in detail using catalogues of galaxy distances and motions, described the result as a system of cosmic watersheds. Galaxies do not simply sit at rest between their neighbours. They move, and the direction and speed of their motion reflects the underlying mass distribution, even where no visible matter is present. The entire local universe is flowing, rivers of galaxies moving along dark matter channels toward concentrations of mass that function as gravitational basins. The cosmic web is not a static structure. It is an active one, continuously channeling matter toward its nodes while evacuating its voids. A subsequent analysis using the Fourth Cosmic Flows catalogue, published by Alexandre Dupuy and Hélène Courtois in Astronomy and Astrophysics in 2023, incorporated approximately 56,000 galaxy distance measurements and confirmed that observed superclusters across the local universe are on average an order of magnitude larger than the standard cosmological model predicts they should be. An order of magnitude is not a refinement. It is a category error, the difference between a structure that fits the model and a structure that the model cannot produce. The cosmic web, in its full observed extent, consistently exceeds what the standard framework generates in simulations calibrated to the known cosmological parameters. What makes this discrepancy particularly difficult to dismiss is that the cosmic web's excess structure appears not only in the size of individual components, but in their connectivity. Simulations of structure formation under lambda, cold dark matter produce filaments that connect clusters over distances of tens to hundreds of millions of light years. The observed filaments, mapped with increasing precision by successive generations of redshift surveys and now probed in the early universe by Webb's spectroscopic programs, show connectivity over distances that push against and occasionally beyond those theoretical limits. A filamentary structure connecting galaxy clusters separated by several hundred million light years was the kind of observation that, appearing in isolation, would attract scrutiny about measurement methodology. Appearing repeatedly across independent surveys, it becomes evidence that the model's description of how structure forms and grows is missing something. Dark matter filaments are not directly imaged. Their presence is inferred from the statistical distribution of the galaxies they contain and from the gravitational lensing they produce on background light. The Subaru Hyper-Suprime Cam survey and the Dark Energy survey, both ground-based programs operating in parallel with Webb's space-based observations, have contributed weak lensing maps of the dark matter distribution across large areas of sky that confirm the filamentary structure independently of galaxy counting. When those lensing maps are compared to the galaxy distribution maps from spectroscopic surveys, the agreement on the existence and approximate location of the filaments is strong. Where the disagreement with theory persists is in the filament sizes, masses, and the epoch at which they became observationally prominent. All three are consistently larger and earlier than the simulations produce. The void we are living inside. The cosmic web's existence implies voids as a structural necessity. Matter cannot accumulate into filaments and nodes without evacuating the regions between them, and the evacuation process, driven by gravity over the full age of the universe, produces volumes of space so depleted of ordinary matter that calling them near empty is not metaphor. The Bootis void, discovered in 1981 by Robert Kirshner at Harvard, during a systematic survey of galaxy redshifts, remains the most extreme confirmed example. Kirshner's team expected galaxies to be distributed with variations across the survey volume, denser in some regions, sparser in others, but generally present throughout. Instead, they found a roughly spherical region approximately 330 million light-years across, containing approximately 60 galaxies, where models of large-scale structure predicted thousands should exist. Kirshner reportedly described the void as so large he was embarrassed to tell people about it. It was too large to fit comfortably within the theoretical framework predicting how voids form and how big they grow. The Bootis void is an extreme outlier. What is more relevant to any assessment of our own situation is evidence that we inhabit a void ourselves, one far larger in scale than the Bootis structure, though less extreme in its degree of underdensity. The structure in question is called the KBC void, named for the researchers who characterized it systematically, Keenan, Barger, and Cowie, in a 2013 paper that attracted limited attention at the time. It describes an underdense region approximately 2 billion light-years across, centered roughly on our local group, within which the average matter density is substantially below the cosmic mean. 2 billion light-years. The Bootis void is 330 million light-years across. The KBC void is 6 times larger in diameter. It encompasses the Laniakea supercluster, which contains the Milky Way, the Andromeda Galaxy, the Virgo cluster, and more than 100,000 other galaxies. It encompasses the Shapley concentration, the densest accumulation of galaxies in the local universe, toward which everything in Laniakea is gravitationally flowing. It encompasses several 100 million light-years of surrounding space in every direction. The reason this matters beyond a description of our address is its connection to the Hubble tension. A region of lower than average density experiences different gravitational dynamics than the cosmic mean. Galaxies inside a void are pulled preferentially toward its walls as the void expands and empties over time, imprinting an additional outward velocity component on their motions beyond the pure Hubble expansion. If the KBC void introduces a systematic boost to the measured recession velocities of nearby galaxies, then the local Hubble constant measurements might read higher than the true global expansion rate, not because any measurement is instrumentally wrong, but because the local universe is genuinely expanding faster than average due to its position inside an underdense region. Whether the KBC void fully accounts for the Hubble tension remains contested. Some analyses find that the underdensity is not pronounced enough to explain the full 5 to 6 sigma discrepancy. Others find that properly modelling the void's influence reduces the tension to levels consistent with remaining systematic uncertainties. What is established beyond dispute is that our position in the large-scale structure of the universe is not a neutral fact. It is a physical circumstance with measurable consequences for what our instruments tell us about the universe's expansion rate. We are measuring the cosmos from inside a bubble, and the bubble is influencing the measurement. The KBC void's existence also complicates the interpretation of every survey of the local universe. Peculiar velocity measurements, redshift surveys, weak lensing maps, all of them are drawn from a sample of the universe that is systematically underdense relative to the cosmic mean. The galaxies being used to calibrate the Hubble constant, to measure dark energy's behaviour, to test models of structure formation, all sit inside a region that may not be representative of the universe as a whole. Whether the statistics can be corrected for this selection bias depends on how accurately the void's density profile, extent, and gravitational influence can be characterized, and that characterization is itself drawn from data inside the void. The problem is not circular in a logically disqualifying sense, but it adds a layer of complexity to the cosmological inference chain that remains incompletely quantified. Every measurement carries its context, and our context is stranger than previously recognized. The void we inhabit also has a boundary, and what lies beyond it is where the more dramatic features of the local, large-scale structure begin. The boundary of the KBC void is not a sharp edge, but a gradient, a region where the density transitions from below average toward the surrounding filaments and clusters. Beyond that transition, matter accumulates into the structures gravity has been building over billions of years, and the most immediate of those structures, the one containing the Milky Way and more than 100,000 of its neighbours, carries a name that was formally established only in 2014. The structure 10 billion light-years long. The cosmological principle is not a hypothesis. It is a foundational assumption built into the mathematical architecture of modern cosmology, present in every equation used to describe the universe at its larger scales. It holds that at sufficiently large scales, the universe is homogeneous, meaning matter is distributed uniformly in all directions, and isotropic, meaning no direction through space is preferred over any other. Without this principle, the equations of general relativity that describe the universe's expansion cannot be solved in their current simplified form, and the entire edifice of precision cosmology, including the Hubble constant, the matter and energy density parameters, and the predictions of the Big Bang model, would require reconstruction from different starting assumptions. The principle is understood to have a scale of applicability. Below roughly 1.2 billion light-years, structures are expected and observed: filaments, voids, clusters, and superclusters of the kind described in the previous chapter. Above that scale, the standard model predicts that the universe averages out, that no coherent structure persists beyond that threshold, and that the distribution of matter becomes statistically uniform when sampled in volumes large enough. This prediction follows directly from the physics of inflation and the subsequent evolution of density fluctuations under gravity. It is not an optional feature of the model. It is a direct theoretical consequence of the known initial conditions and the time available for gravity to act on them. In 2013, a team led by István Horváth at the National University of Public Service in Hungary, working with John Hakila at the College of Charleston and Zsolt Bogoli, detected a statistically significant clustering of gamma-ray bursts spanning an angular extent that translated at the inferred distances of the objects to a physical scale of approximately 10 billion light-years in length and roughly 7.2 billion light-years in width. The structure was named the Hercules Corona Borealis Great Wall, after the constellations it spans across the northern sky. The finding was published and drew attention from specialists in large-scale structure, but did not immediately enter broader cosmological discussion as a settled structural detection. Gamma-ray burst positions carry their own measurement uncertainties, and the clustering statistics required careful treatment to rule out instrumental or selection biases. In April 2025, an expanded analysis revisited the original detection with a substantially larger gamma-ray burst catalogue accumulated over the intervening years. The structure was confirmed at increased statistical significance. Its estimated physical extent had not shrunk under the expanded dataset. If anything, the boundaries appeared larger than the initial estimate had suggested. The Hercules Corona Borealis Great Wall spans approximately 10% of the diameter of the entire observable universe. It is 8 times larger than the theoretical maximum size at which coherent structure can persist under the cosmological principle. The scale requires a specific framing to convey accurately. The Bootes void, discussed in the previous chapter as so large its discoverer was embarrassed to report it, measures approximately 330 million light-years across. The Sloan Great Wall, discovered in 2003 through the Sloan Digital Sky Survey and regarded at the time of its discovery as pushing the boundary of what the model allowed, spans approximately 1.37 billion light-years. The Boss Great Wall, identified in 2016, reaches approximately 1 billion light-years. These structures cluster near the cosmological principle's predicted upper limit, straining it in some analyses, but not unambiguously violating it given measurement uncertainties. The Hercules Corona Borealis Great Wall is not near the limit. It exceeds it by a factor of 8 in a direction and by a magnitude that no adjustment to measurement methodology has been able to eliminate. The theoretical implications are specific and serious. A structure of this size cannot have assembled through the gravitational amplification of early density fluctuations in the time available since the Big Bang, under the Standard Model's description of those fluctuations and of how gravity has acted on them. The density fluctuations produced by inflation are constrained by the cosmic microwave background measurements to be small and nearly scale invariant, meaning they do not contain the power at large scales required to produce a coherent structure 10 billion light-years across. Growing such a structure through gravitational instability from those initial conditions in 13.8 billion years is not merely improbable under the Standard Model. It is not what the Standard Model produces under any plausible variation of its parameters. The options available to the field are limited. Either the detection contains an unidentified systematic error that has survived 2 independent analyses conducted 12 years apart using expanded datasets, or the cosmological principle fails at scales larger than the model predicted. The first option cannot be ruled out with current data. Gamma-ray burst samples, while large, carry redshift uncertainties that complicate clustering statistics at extreme scales. But no specific systematic error has been identified that would produce the observed clustering signal. The second option requires the most fundamental assumption in modern cosmology to be wrong about the scale at which it applies. Both possibilities are uncomfortable in different ways, and the field has not resolved the choice between them. What the James Webb Space Telescope has contributed to this picture is corroborating evidence at smaller scales that large-scale structure is consistently more organised and more extended than the standard model produces. The early galaxy surpluses, the oversized superclusters from the cosmic flows analysis, and the Hercules Corona Borealis Great Wall all point in the same direction. The universe organised itself more efficiently, at larger scales, and earlier than any simulation built on the standard cosmological parameters has managed to reproduce. There is a deeper theoretical issue embedded in the Hercules Corona Borealis Great Wall that connects to every other anomaly the telescope has revealed. The density fluctuations produced by inflation, which seeded all subsequent structure formation, are constrained in their statistical properties by the cosmic microwave background measurements. Specifically, they are predicted to follow a nearly scale invariant power spectrum, meaning fluctuations of different sizes all start with roughly similar amplitudes at the moment of inflation. As gravity amplifies these fluctuations over time, the power spectrum evolves, with small scales becoming nonlinear, meaning they collapse into bound structures before large scales do. A structure 10 billion light years across would require power at that scale in the initial fluctuation spectrum far exceeding what the scale invariant prediction provides, and far exceeding what the cosmic microwave background measurements constrain to be present. There are theoretical models that depart from scale invariance at large scales, introducing additional power that could produce larger coherent structures. Some inflationary models with specific features in the potential energy function produce so-called running of the spectral index, a scale dependence of the power spectrum amplitude that increases power on large scales relative to the simplest prediction. But matching the Hercules Corona Borealis Great Wall requires departures from scale invariance so large that they should also produce visible effects in the cosmic microwave background at the largest angular scales, effects that the Planck data does not show at the required level. Threading a modification to inflation that produces the observed structure without violating the microwave background constraints is a constrained and currently unsolved theoretical problem. The anomaly is not just an observational oddity. It is a constraint on whatever physics might explain it, and the constraint is tight. What lambda cold dark matter actually predicts and why that matters. Lambda cold dark matter is not a rough sketch or a working hypothesis. It is the most precisely tested theoretical framework in the history of cosmology, refined over 4 decades through observations spanning 13 orders of magnitude in physical scale, from the fluctuations in the cosmic microwave background at scales of billions of light years to the distribution of dark matter substructure within individual galaxies measured in kiloparsecs. Its 2 central components, the cosmological constant lambda, representing dark energy, and cold dark matter as the dominant gravitating substance in the universe, each have independent observational support from multiple entirely different measurement techniques. The model is not a guess that happened to survive scrutiny. It is a framework that passed every observational test put to it for decades. The lambda in the name refers to the cosmological constant, the term Einstein introduced into his equations of general relativity in 1917, and later called his greatest blunder, when Edwin Hubble's observation showed the universe was expanding rather than static. The constant was rehabilitated in 1998, when Adam Riess, Saul Perlmutter, and Brian Schmidt independently discovered, through measurements of type Ia supernovae at cosmological distances, that the universe's expansion is not merely continuing, but accelerating. A decelerating universe expected under a matter-dominated model without a cosmological constant would cause distant supernovae to appear brighter than their redshifts predicted. The observed supernovae appeared fainter, meaning they were farther away than expected, meaning the expansion was accelerating. The cosmological constant reinterpreted as the energy density of empty space, was the simplest explanation for the acceleration, and it has remained the standard description of dark energy ever since. The cold in cold dark matter refers to the velocity distribution of the dark matter particles at the time of structure formation. Cold dark matter particles move slowly relative to the speed of light at the epoch, when they begin to gravitationally cluster. This property determines the characteristic scale at which dark matter halos first form. Small halos form first because small scales become gravitationally unstable first, and larger structures assemble later through hierarchical merging. Hot dark matter, particles moving near the speed of light at the relevant epoch, would free stream out of small density fluctuations before they could collapse, producing a different large-scale structure pattern, with large structures forming first and small structures fragmenting later. The observed large-scale structure of the universe, with its small galaxies and galaxy groups embedded in a web of larger clusters and superclusters, favours the cold dark matter scenario strongly over the hot alternative. The model's predictions for the cosmic microwave background temperature fluctuation spectrum match the Planck satellite measurements with extraordinary precision across many independent acoustic peaks, the oscillations in the power spectrum that reflect the physics of the photon-baryon fluid before recombination. Matching all of those peaks simultaneously at the correct relative amplitudes and positions constrains the cosmological parameters, including the Hubble constant, the matter density, the dark energy density, and the curvature of space to percent-level precision. This is not an approximation. It is one of the most precisely constrained physical measurements in all of science. What makes the James Webb Space Telescope's results troubling is not that they contradict a model that was loosely supported. They contradict a model that was precisely supported. Every anomaly the telescope has revealed represents a departure from predictions that the Planck measurements and decades of large-scale structure surveys had confirmed to be correct in other regimes. The galaxies that are too massive, the black holes that are too old, the structures that are too large, all arise in a regime the model predicted specifically. Using parameters constrained by data it also predicted correctly. The model cannot be wrong only about the early universe while remaining perfectly correct about everything else it describes, because the early universe is where the initial conditions originated from which everything else evolved. An error in the early universe description propagates forward through cosmic time and must eventually show up in the local universe, which has been measured precisely enough to constrain any correction. Threading a revision that fixes the early galaxy problem without breaking the local universe measurements is one of the most constrained theoretical challenges currently facing the field. One specific mechanism that has received serious theoretical attention is a modification to the dark matter model. Lambda, cold dark matter, assumes dark matter consists of particles that were non-relativistic at the time of structure formation and interact with ordinary matter only through gravity and possibly the weak nuclear force. This description is generic. It does not specify the mass of the dark matter particle, its production mechanism, or its detailed interaction cross-section, beyond requiring that these properties produce the observed power spectrum of density fluctuations. Alternatives that have been proposed to address the early galaxy problem include warm dark matter, in which the particles have a small but non-zero thermal velocity that suppresses structure formation below a characteristic scale, potentially reducing the number of early low-mass halos and changing the conditions under which the first galaxies form. Another alternative is fuzzy dark matter, a model in which the dark matter consists of ultralight axion-like particles with a de Broglie wavelength comparable to the size of dwarf galaxies, producing a suppression of small-scale structure through quantum mechanical effects rather than thermal motion. A third alternative invokes self-interacting dark matter, particles that scatter off each other through a new force, potentially changing the density profiles of dark matter halos in ways that affect galaxy formation. None of these alternatives has been shown to simultaneously resolve the early galaxy mass problem, match the cosmic microwave background constraints, reproduce the observed statistics of large-scale structure at intermediate redshifts, and remain consistent with direct detection experiments that have so far found no dark matter particles. Each addresses some aspect of the discrepancy while introducing tensions elsewhere. The theoretical landscape is rich and the constraints are tight, which means that the observational data the James Webb Space Telescope is producing is not just documenting anomalies, but actively constraining the space of possible resolutions. Each new measurement from the telescope narrows the range of theoretical modifications that can survive it, and the process of elimination, though slow, is advancing with every observing cycle. Dark energy is not behaving the way we assumed. The cosmological constant describes dark energy as a fixed property of empty space, a constant energy density that does not dilute as the universe expands, does not vary from place to place, and does not change over time. Under this description, dark energy was the same in the early universe as it is today, the same in dense regions as in voids, the same yesterday as it will be a billion years from now. This constancy is not incidental to the model. It is what makes dark energy mathematically equivalent to a vacuum energy, a ground state energy of the quantum fields filling empty space, and it is what allows the cosmological constant to be characterized by a single number rather than a function that evolves. On April 4, 2024, the Dark Energy Spectroscopic Instrument Collaboration released results from its first year of observations that challenge this picture directly. The instrument, mounted on the Mile 4-meter telescope at Kitt Peak National Observatory in Arizona, measured the redshifts of more than 6 million galaxies during its first year, producing the most detailed three-dimensional map of the large-scale structure of the universe ever assembled. The survey was designed specifically to measure baryon acoustic oscillations, the same acoustic peaks visible in the cosmic microwave background, but imprinted in the three-dimensional distribution of galaxies across cosmic time. Because baryon acoustic oscillations have a known physical scale, they serve as a standard ruler, allowing the survey to measure how the universe's expansion rate has changed at different epochs and thereby characterize dark energy's behavior across cosmic history. The results from the Dark Energy Spectroscopic Instrument, when combined with measurements from the Planck satellite's cosmic microwave background analysis and supernova surveys including the Dark Energy Survey, showed a deviation from the cosmological constant at a statistical significance of 3.9 sigma. Dark energy's behavior had changed over the universe's history. The simplest model, which required it to be constant, was inconsistent with the combined dataset at a level that would be considered significant by the standards of most scientific fields. Michael Levi, the director of the Dark Energy Spectroscopic Instrument Project, stated publicly that the data raised the possibility that dark energy had evolved over time. A separate analysis published in Physical Review D in September 2025 by Anik Woyer Jaman Shajib at the University of Chicago and collaborators found, using an independent dataset and methodology, that dark energy appeared to have decreased in strength by approximately 10% over recent cosmic history, at a confidence level of 99.6%. The baryon acoustic oscillation measurements that provide the Dark Energy Spectroscopic Instrument's primary constraint on dark energy work through the following logic. In the early universe, before recombination, ordinary matter and radiation were coupled into a photon-baryon fluid that oscillated under the competing forces of radiation pressure pushing outward and gravity pulling inward. These oscillations, propagating through the primordial plasma at roughly half the speed of light, imprinted a characteristic scale into the distribution of matter at recombination, when the plasma cooled enough for electrons to combine with protons into neutral hydrogen and the photons decoupled and streamed freely. That characteristic scale, approximately 150 megaparsecs in co-moving units, is preserved in the distribution of galaxies throughout cosmic time and is detectable as a preferred separation distance in galaxy surveys. Because the physical scale is set by known early universe physics, measuring the angular size of this feature at different redshifts provides a direct measurement of the expansion history. Comparing the measured angular sizes at multiple epochs tells you how the expansion rate changed over cosmic history, and the rate of change constrains dark energy's equation of state as a function of time. The dark energy spectroscopic instrument achieved the statistical precision needed to detect the evolution of the equation of state because it measured baryon acoustic oscillations at multiple distinct redshift intervals, providing a time-resolved history of dark energy's influence rather than a single integrated measurement. The departure from a constant equation of state appeared most clearly in the comparison between low redshift measurements, where dark energy dominates the expansion, and intermediate redshift measurements, where matter and dark energy contribute more comparably. The evolution implied by the data is not dramatic in percentage terms. Dark energy has not changed by orders of magnitude. But in a universe where the cosmological constant was supposed to be exactly constant, a 10% change measured at 99.6% confidence is the difference between a fundamental property of space-time and a dynamical field with its own physics and evolutionary history. The implications of a changing dark energy are not incremental. Dark energy comprises approximately 68% of the total energy content of the universe. Ordinary matter, everything that has ever been observed, measured, or theorized in the history of physical science, constitutes roughly 5%. Dark matter accounts for roughly 27%. Dark energy is the dominant component, and the ultimate fate of the universe depends on its behavior. A constant dark energy drives eternal accelerating expansion, eventually separating all galaxies beyond the local group across a cosmic event horizon. A weakening dark energy could allow gravity to eventually decelerate and reverse the expansion. A strengthening dark energy could accelerate the expansion without limit, leading to an outcome where the repulsive force eventually overwhelms the forces binding galaxies, then stars, then planets, then atoms themselves. The confirmation that dark energy's strength has measurably changed over cosmic history rules out the simplest description of what it is. A true cosmological constant, a fixed energy density of the vacuum, cannot change. Any physical mechanism capable of producing a dark energy that changes must involve a field that evolves through time, rather than a static property of empty space. Identifying such a field, understanding its origin, and predicting how it will continue to evolve are open problems for which no consensus solution exists. The phantom divide and what crossing it means. The behavior of dark energy is encoded in a single parameter that cosmologists call the equation of state, typically written as the letter W. It describes the ratio of dark energy's pressure to its energy density, a relationship that in ordinary matter is always positive, but in dark energy must be negative to produce the observed accelerating expansion. For the cosmological constant, W equals -1 exactly. This is not an approximation or a best fit value. It is an exact consequence of the mathematical properties of a fixed vacuum energy density. Values of W greater than -1 describe a dark energy that weakens over time as the universe expands. The energy density decreases as the volume of space grows, and the acceleration of expansion is maintained but does not intensify. At W equal to -1, the energy density stays constant regardless of volume. For values of W less than -1, the situation becomes qualitatively different in a way that the name phantom energy captures accurately. A phantom dark energy does not dilute as the universe expands. It grows denser. As space expands and the volume increases, the total dark energy in that larger volume is greater than it was before. The repulsive force accelerates the expansion, which expands the volume further, which increases the dark energy, which accelerates the expansion faster. The feedback loop has no natural ceiling. A universe with phantom dark energy does not simply expand forever in a cold, gradual way. The expansion accelerates without limit. Structures that are currently gravitationally bound will eventually find themselves in a universe expanding fast enough to overcome the forces holding them together. The sequence of destruction that follows has been calculated in detail. Approximately 2 billion years before the end of the universe in this scenario, the expansion rate exceeds the gravitational binding energy of galaxy clusters, and they begin to disperse. 60 million years before the end, the expansion overcomes the self-gravity of individual galaxies, and the Milky Way's structure is destroyed. 3 months before the final moment, the expansion overwhelms the gravitational pull of our star on its planets, and the solar system is dismembered. 30 minutes before the end, Earth's structural integrity fails, as the expansive force exceeds the electromagnetic forces holding rock together. In the last fractions of a second, individual atoms are pulled apart as the repulsive force reaches the scale of nuclear binding energies. The universe ends not in cold silence, but in a total simultaneous dissolution of every structure at every scale, from galactic down to subatomic. This outcome has a name: the Big Rip. The dark energy spectroscopic instrument data introduced a specific complication into this picture. William Elbers at Durham University and colleagues analysing the instrument's results in combination with multiple other surveys found evidence that dark energy's equation of state had crossed the phantom divide, the boundary at T equal to -1. The data suggested that dark energy behaved as phantom energy in the past, with W below -1, but has since weakened and now sits above that threshold. Elbers stated the situation plainly. Dark energy appeared to have been phantom in the past, but was no longer phantom today, and the simplest theoretical descriptions of dark energy do not allow for that kind of behaviour. This is a technically precise statement about a deep theoretical constraint, a single scalar field, the kind of dynamical dark energy model most commonly invoked as an alternative to the cosmological constant, cannot cross the phantom divide. The mathematical properties of a real scalar field constrain its equation of state to remain on one side of -1. Crossing the divide requires either two interacting fields, one of which has a negative kinetic energy, or some other theoretical structure that introduces significant additional complexity and its own theoretical problems. The data appeared to be describing a dark energy that had done something the simplest theoretical framework said it could not do. If the result holds under continued scrutiny, the already uncertain question of dark energy's nature becomes substantially more constrained in a direction that rules out the most commonly proposed alternatives, leaving the field without a consensus description of what the dominant energy component of the universe actually is. The 5-galaxy merger that rewrote the early universe timeline. In February 2026, a team led by Wida Rujapakar at Texas A&M University announced that the James Webb Space Telescope had detected 5 galaxies in the process of merging approximately 800 million years after the Big Bang. The observation required some of the telescope's deepest exposures in a region of sky where spectroscopic data had already confirmed the presence of several high redshift objects. The redshifts of all 5 galaxies were consistent with a single epoch, placing them in a physically associated system rather than a chance alignment of objects at different distances along the line of sight. The merger was directly visible in the data. 5 distinct galactic structures with overlapping stellar populations, deformed halos, and tidal features indicating active gravitational interaction rather than a fortuitous proximity. The combined system was producing approximately 250 new stars per year, each carrying the mass of a typical star. The current Milky Way produces between 1 and 3 new stars per year across its full extent. The ancient five-way merger was generating stellar mass at roughly 100 times the rate of our own galaxy, concentrated into a single interacting system occurring when the universe was barely 6% of its current age. Rujapa Khan stated directly that a merger involving this many galaxies was not expected to occur so early in cosmic history under any existing theoretical framework. The statement is precise, not merely unexpected in the sense of being surprising, but inconsistent with what the framework produces when its parameters are set to match all the other observations it successfully describes. Lambda cold dark matter predicts that galaxy mergers should be common in the early universe because the hierarchical assembly process requires small structures to combine into larger ones. But a five-way merger of galaxies massive enough to contain substantial stellar populations at a redshift of approximately 7 falls outside the statistical tail of what the model's merger rates and galaxy mass functions predict at that epoch. The probability is not negligible, but it is low enough that seeing one in a survey area the size of the JADES field, rather than in a survey orders of magnitude larger, indicates the underlying rate is higher than the model generates. The chemical context of this observation matters as much as the merger itself. Oxygen was detectable in the merger system's light. The same tracer of stellar nucleosynthesis discussed in the context of JADES GS Z110 at 290 million years was present at 800 million years in a system of 5 interacting galaxies, each having already processed gas through one or more generations of massive stars and supernova explosions. By 800 million years, the oxygen detection is less surprising in absolute terms than at 290 million years, but still significant in what it confirms about the pace of chemical evolution in the early universe. Star formation in these systems was not beginning at 800 million years. It had been underway for long enough that the chemical enrichment signature was already measurable, meaning the galaxies involved in this merger had substantial prior star formation histories extending well before the observed epoch. Galaxy mergers are the mechanism by which galaxies grow beyond the sizes achievable by smooth gas accretion alone. Each merger event funnels gas toward the centers of the colliding systems through tidal torques and gravitational shocks, compressing star-forming clouds and triggering bursts of star formation at rates far above what quiescent accretion sustains. The merger also drives gas toward the central black holes of both galaxies, triggering active galactic nucleus phases during which the black holes grow rapidly. The simultaneous intensification of star formation and black hole growth during mergers provides a natural physical context for the little red dots described in an earlier chapter. Objects in which both the stellar mass and the black hole mass were growing at extreme rates in an environment where mergers were frequent. If five-way mergers were occurring at 800 million years in numbers large enough to be detected in a narrow survey field, the supply of merger-driven gas feeding both processes was not a rare luxury in the early universe. It was the standard operating condition. The broader implication of the Rujapa Khan team's finding concerns the relationship between the early merger rate and the galaxy mass function at later epochs. In the standard hierarchical model, the massive galaxies observed in the present-day universe assembled their stellar populations gradually, through a combination of in situ star formation from accreted gas and ex situ growth through the absorption of smaller galaxies over billions of years. The most massive elliptical galaxies in present-day clusters containing between 100 billion and several trillion solar masses in stars, are understood to be the end products of this long assembly process. The progenitors of these massive systems should be visible at high redshift as moderately massive galaxies in the process of assembly, not yet at their final mass, still actively forming stars. The five-way merger at 800 million years represents a system already containing substantial stellar mass across 5 distinct galaxies, merging in a single event that will produce a combined system more massive than any of its components. If such mergers were common at that epoch, the assembly of massive galaxies was accelerated relative to what the standard hierarchical model predicts. Fewer, larger mergers occurring earlier, rather than many small mergers accumulated gradually over billions of years. This would shift the expected mass distribution of galaxies at intermediate redshifts in a direction consistent with what surveys have observed. Too many massive galaxies at redshifts between 2 and 6 assembled too early and too completely to fit the gradual hierarchical picture. The five-way merger is not an isolated curiosity. It is a data point in a larger pattern of early assembly that the telescope has been revealing consistently since its first science year. How the universe builds order through catastrophe. Every structure in the observable universe is the product of a process that involves destruction as much as construction. The cosmic web formed because density fluctuations that were slightly overdense collapsed, and the regions surrounding them were evacuated. Galaxy clusters grew by consuming smaller galaxy groups. Individual galaxies accumulated mass by cannibalizing companions, tidally stripping stars from neighbors, and absorbing the debris of collisions accumulated over billions of years. The stars those galaxies contain were forged in the violent collapse of molecular cloud cores, processes that fragment and destroy the clouds in which they occur. The planets around those stars assembled from material that had been processed through at least one prior generation of stellar death. The entire hierarchy of cosmic structure, from the largest filaments to the smallest rocky worlds, represents order extracted from catastrophe rather than order built by orderly accumulation. The James Webb Space Telescope has documented this character of cosmic construction most clearly in its observations of the early universe, where the violence was most concentrated and the pace of events most compressed. The five-way merger at 800 million years is one data point in a larger pattern. The telescope's deep surveys have revealed protoclusters, dense concentrations of galaxies in the process of assembling into galaxy clusters, at redshifts above 6, corresponding to less than 1 billion years after the Big Bang. These protoclusters are themselves dynamic environments, multiple galaxies undergoing simultaneous starbursts, several showing evidence of active galactic nucleus activity, the whole system embedded in a dense gas reservoir that feeds both processes. The rate of star formation in these early protoclusters exceeds what any similar structure in the present-day universe produces. The first stars that ended the cosmic dark ages, forming between roughly 100 and 200 million years after the Big Bang, were themselves agents of catastrophe. They formed from gas that contained nothing heavier than helium and trace lithium, a composition that affected their masses profoundly. Without the carbon and oxygen atoms that mediate the cooling of molecular clouds in the present universe, the first star-forming clouds could not fragment as finely, and the resulting stars were likely far more massive than typical present-day stars. Theoretical models of population 3 star formation, as these first stars are designated, suggest that individual stellar masses may have reached hundreds of solar masses or more, objects that would be extraordinarily rare in the contemporary galaxy. Stars that massive live for only a few million years before exhausting their fuel and either collapsing directly into black holes without a conventional supernova or exploding as pair instability supernova, the most energetic category of stellar explosion, releasing energy comparable to thousands of ordinary core collapse supernova in a single event. A pair instability supernova leaves no compact remnant. The star is completely disrupted, and its nuclear products, including substantial quantities of oxygen, silicon, calcium, and iron group elements, are distributed into the surrounding gas at high velocity. A single such explosion can chemically enrich a volume of the early universe comparable to a small protogalaxy. The second generation of stars forming from this enriched gas would find the cooling channels opened by carbon and oxygen, allowing their birth clouds to fragment more finely and produce a range of stellar masses more similar to what we observe in the present universe. Chemical evolution in the early universe was therefore self-accelerating. The first massive stars produced the heavy elements that enabled the second generation to form more efficiently, which produced more enrichment, which enabled more efficient subsequent star formation. This cascade is the physical underpinning of the oxygen detection at 290 million years. The enrichment required to produce measurable oxygen abundance in JADES GS Z5.0 implies that this self-accelerating cycle was already well advanced within the first few 100 million years. The early universe was not a gentle cradle where the first faint embers of star formation slowly brightened over hundreds of millions of years. It was an environment where the first violent stellar deaths immediately created the conditions for the next cycle, compressing what the standard model described as a leisurely, hierarchical build-up into a rapid, self-sustaining cascade of formation and destruction that assembled chemically complex, structurally mature galaxies in a fraction of the time the models predicted. The Milky Way itself bears the chemical record of this early violence. Its older stars, members of the stellar halo population, with ages approaching 13 billion years, show chemical abundance patterns that encode the products of the first stellar generations. High-resolution spectroscopy of these halo stars has revealed objects whose iron content is millions of times lower than the Sun's, meaning they form from gas that had experienced very little prior stellar processing, and whose ratios of oxygen to iron, calcium to iron, and silicon to iron match the theoretical yields of massive early supernovae. These stars are fossils. They have been orbiting the galaxy for nearly as long as the galaxy has existed, and their chemical compositions are direct records of what was happening in the universe before our solar system existed. The discovery of extremely metal-poor stars in the halo, some with iron abundances more than 1 million times lower than the solar value, has allowed astronomers to partially reconstruct the properties of the first stellar generations that died before any surviving star existed to record them. The technique, called stellar archaeology or near-field cosmology, uses the chemical abundances measured in ancient halo stars as indirect probes of the yields from the early supernovae that enriched the gas from which those ancient stars formed. Different types of supernovae, core collapse events from stars of different masses, pair instability events from the most massive first-generation stars, and the rare class of hypernovae with explosion energies 10 to 100 times above normal, each produce different ratios of carbon, oxygen, magnesium, silicon, calcium, and iron. By measuring these ratios in extremely metal-poor halo stars with sufficient precision, researchers can in principle identify which type of supernova contributed most of the heavy elements in those stars' birth gas cloud. The results of this stellar archaeology, accumulated over 2 decades of high-resolution spectroscopic surveys, are consistent with a picture in which the very first supernovae were energetic, massive, and chemically productive. The abundance patterns in the most ancient metal-poor stars match theoretical yields from core collapse supernova of massive progenitors and, in some cases, from pair instability events associated with the very highest mass range of first-generation stars. This ground-based observational program is entirely consistent with what the James Webb Space Telescope has revealed from the other direction, a universe in which the first stars were massive, short-lived, and chemically prolific, and in which the enrichment they produced fueled a rapid escalation of star formation efficiency that assembled chemically complex galaxies far faster than the standard model predicted. The observable horizon and what lies beyond it. The James Webb Space Telescope can see further into the universe's history than any instrument that preceded it. It cannot see all of history, and it cannot see all of space. The boundary of what is observable from Earth is not a wall or a surface of any physical kind. It is a consequence of the finite speed of light and the finite age of the universe. Light from objects more distant than a certain threshold has not had time to reach us since those objects first emitted it. And in many cases, the expansion of space between them and us is carrying them away faster than their light can close the gap. The observable universe has a radius of approximately 46.5 billion light-years, meaning the most distant objects we can in principle detect are currently that far away. The number is larger than the 13.8 billion-year age of the universe expressed in light-years, because the space between us and those distant regions has been expanding throughout the time their light has been travelling toward us. The objects that emitted the cosmic microwave background radiation, the oldest light we can detect, were approximately 42 million light-years away when they emitted it. They are now approximately 46 billion light-years away. Their light has been travelling toward us for 13.8 billion years, while the space it traversed stretched. Beyond the observable universe, space continues. There is no physical boundary, no wall, no edge. The universe is simply larger, possibly vastly larger than the portion whose light has had time to reach us. What fraction of the total universe our observable region represents is a question that cannot be answered directly, because the regions beyond our horizon cannot be observed and their extent cannot be measured. What can be estimated is a lower bound, using observations of the universe's geometry combined with models of its total extent. Mikhail Vardanyan at Oxford, Roberto Trotta at Imperial College London, and Joseph Silk at Johns Hopkins University applied Bayesian model averaging to the available cosmological data and published their analysis in 2011. Their conclusion was that the total universe is at minimum 250 times larger in volume than the observable portion. Alternative analyses using updated data have produced estimates ranging from several hundred times larger to, in the case of a spatially flat infinite universe, a total extent that is literally infinite. The Planck measurements favour a geometry close to flat, and a precisely flat universe is infinite in spatial extent by definition. Whether the universe is exactly flat or only very nearly flat makes a dramatic difference. Slightly curved and finite versus flat and infinite. Current measurements cannot distinguish between these cases at the required precision. 250 times larger in volume means a minimum total diameter of roughly 23,000 billion light-years if the universe is finite and spherical. If it is flat and infinite, the diameter is not a meaningful concept. What this implies for the James Webb Space Telescope's results is specific and sobering. Every galaxy, every black hole, every merger system, every structure that has challenged the standard model's predictions exists entirely within a bubble that represents at most 1/250th of the universe's actual extent, and possibly an incomprehensibly smaller fraction of an infinite whole. The cosmological models built on the telescope's data and on all the data that preceded it are models of this small region. Whether the processes that produced the early galaxy surplus, the little red dots, and the Hercules Corona Borealis Great Wall are representative of what happens throughout the universe cannot be determined, because the rest of the universe is permanently inaccessible. The sample from which all of cosmology's inferences are drawn is at minimum 250 times smaller than the population it is assumed to represent. Whether that sample is typical or atypical, whether our observable bubble Is a representative corner of the universe or an unusual one is a question that no observation, however advanced, will ever resolve. There is a further level to this inaccessibility that is worth specifying precisely. When cosmologists talk about the universe beyond the observable horizon, they are referring to regions where the physics is expected to be the same constants of nature, the same particle physics, the same forces, the same dark matter and dark energy. This expectation is reasonable but unverifiable. If inflation produced a universe substantially larger than our observable region, and if the inflationary dynamics allow for variation in physical constants across regions separated by distances larger than our observable horizon, then the observable universe may not be representative in a deeper sense than mere statistical sampling. The values of the cosmological parameters that appear in the Planck measurements, including the matter density, the dark energy density, and the Hubble constant itself, might not be universal constants, but local values that differ in other regions of a larger whole. This is the landscape of string theory and eternal inflation, a theoretical framework with genuine problems of predictability and testability. But its existence as a serious theoretical possibility underlines the fundamental limit of what any observation confined to a single bubble in a much larger universe can determine about the nature of reality. The James Webb Space Telescope is operating within that bubble. Everything it has revealed, every tension it has sharpened, every standard model prediction it has challenged, applies to the observable universe and nothing beyond it. That scope is simultaneously everything we have ever known and a vanishingly small sample of the whole. Both things are true at once, and neither cancels the other. The closing window of cosmic legibility. The horizon that limits our view of the universe is not static. As dark energy drives the universe's expansion to accelerate, galaxies beyond a certain distance are receding from us faster than the speed of light. This does not violate special relativity, which constrains the velocity of objects moving through space, not the rate at which space itself can expand. But the consequence is the same. Light emitted by galaxies beyond the cosmic event horizon will never reach us, regardless of how long we wait. Every second, more galaxies cross that threshold and become permanently inaccessible to any observation. The cosmic event horizon is not the same as the edge of the observable universe. The observable universe is bounded by the look-back time horizon. We can only see light that has had 13.8 billion years to travel. The cosmic event horizon is bounded by the expansion rate. It encompasses all galaxies whose recession velocity, due to the expansion of space between us and them, is slower than light. Currently, the cosmic event horizon sits at approximately 16 billion light-years from Earth. Any galaxy currently beyond that distance will never send us another photon that reaches us. Any galaxy within it is still, in principle, reachable by light and communication, though the practical travel time makes that reachability astronomical rather than useful. Over the next approximately 100 billion years, the galaxies currently within the observable universe, but outside the local group, the several dozen gravitationally bound galaxies within a few million light-years of the Milky Way, will progressively cross the cosmic event horizon as the accelerating expansion carries them away. Within roughly 100 billion years, all external galaxies will have crossed the threshold. The sky will still contain stars, burning in the merged remnant of the Milky Way and Andromeda and their companions. But no galaxy beyond that gravitationally bound local group will be detectable by any instrument. The cosmic microwave background radiation, currently observable as a uniform thermal glow at a temperature of 2.7 degrees above absolute zero, will be stretched by continued expansion to wavelengths too long to detect with any physically realizable instrument. The evidence it carries about the Big Bang, about recombination, about the acoustic oscillations that constrain the cosmological parameters with such extraordinary precision will become unreadable. The redshifts of distant galaxies that establish the expansion history of the universe will be inaccessible because the galaxies will be gone from view. Lawrence Krauss at Arizona State University and Robert Scherer at Vanderbilt University described the consequences for a hypothetical future civilization in a paper published in 2008. A civilization arising 100 billion years from now would find the sky populated only by the stars of the merged local group remnant. They would have no external galaxies to observe, no cosmic microwave background detectable, no expansion to measure, and no redshift data from which to infer the universe's history. Applying science correctly to the evidence available to them, they would likely conclude that the universe consisted of a single large stellar system adrift in infinite static space. The entire conceptual history of modern cosmology, from Hubble's discovery of galactic recession to the James Webb Space Telescope's catalogue of objects at redshift 4, would be unavailable to them and unreconstructible from any evidence they could gather. The implication is that we currently inhabit the only window in cosmic history during which the universe's full past is legible. The cosmic microwave background is still detectable. Galaxies at redshift 14 are still visible. The expansion history is measurable across nearly the full age of the universe. The chemical enrichment history is readable in the spectra of galaxies at every epoch from 290 million years to the present. This window will not remain open indefinitely. The closing is not imminent on any human timescale, but it is physically guaranteed on a cosmological one. The James Webb Space Telescope did not arrive early. It arrived in the last era during which building the complete picture is possible. 3 endings and why we cannot choose between them. The fate of the universe depends on the behaviour of dark energy, and the behaviour of dark energy is not known. This is not a statement about a gap in knowledge that could be filled by collecting more data of the same kind. It is a statement about a fundamental uncertainty at the level of what dark energy physically is, which determines how it will evolve, which determines what happens to the universe over the next tens of billions of years. 3 scenarios remain in play simultaneously, each supported by different subsets of the observational evidence, each producing an ending of such totality that the word ending itself underrepresents what it describes. The first scenario is heat death, also called the Big Freeze. Under this scenario, dark energy remains constant or weakens slowly enough over cosmological time that the expansion continues indefinitely without reversing. Galaxies beyond the local group disappear across the cosmic event horizon within 100 billion years. The stars in the local group remnant exhaust their nuclear fuel over the following tens of trillions of years, cooling progressively as hydrogen is consumed, and stellar populations shift toward lower mass, longer-lived stars. The last red dwarf stars, burning at a fraction of the Sun's luminosity, will exhaust their fuel in roughly 100 trillion years. After that, the local group contains only stellar corpses, white dwarfs cooling toward absolute zero, neutron stars spinning down, and black holes. If protons are unstable, as grand unified theories of particle physics predict, they will decay over timescales of roughly 10 to the power of 34 years, converting the white dwarfs and neutron stars into radiation, and eventually leaving only black holes. The black holes themselves evaporate through Hawking radiation, a quantum process by which the intense curvature of space-time near a black hole's event horizon produces pairs of particles, one of which escapes while the other falls in, gradually reducing the black hole's mass. A black hole with the mass of the Sun takes roughly 10 to the power of 67 years to evaporate in this way. Supermassive black holes of 1 billion solar masses require roughly 10 to the power of 99 years. After the last black hole evaporates, the universe contains only a dispersing gas of photons and the lightest particles, all at effectively zero temperature, distributed across a volume so vast that any local fluctuation above absolute zero is separated from any other by distances light cannot traverse in any remaining time. Maximum entropy. No further organized process is possible. This state continues without change, literally forever, because there is no end state beyond it. The second scenario is the Big Rip. This outcome follows from a dark energy whose equation of state GW is less than -1, the phantom regime described in the previous chapter. The dark energy spectroscopic instrument data suggested the universe passed through a phantom phase in its past. If that phase returns, or if the current equation of state is already below -1 within the measurement uncertainties, the repulsive force grows without limit as the universe expands. Galaxy clusters lose gravitational cohesion approximately 2 billion years before the end. The Milky Way structure is destroyed 60 million years before the end. The solar system is dismembered 3 months before the end. Earth is pulled apart 30 minutes before the final moment. Individual atoms are ripped apart in the last fractions of a second. Unlike the Big Freeze, the Big Rip has a finite endpoint, a specific moment at which everything that exists is simultaneously destroyed at every scale from galactic to subatomic. The third scenario is the Big Crunch, revived from its pre-1998 status as the consensus future of the universe by Henry Tye at Cornell University, who published an analysis in the Journal of Cosmology and Astroparticle Physics in September 2025, proposing that the cosmological constant, rather than being a fixed positive value, represents a metastable vacuum state that is evolving. In his model, the effective cosmological constant emerges from a landscape of possible vacuum states and is negative at its fundamental level. The universe's current phase of accelerating expansion is a temporary condition, like a ball resting partway up a hill rather than in its lowest energy valley. The expansion will continue for approximately 11 more billion years before the dynamics reverse. From that point, contraction begins, slow initially and then accelerating, compressing all existing structures back toward a singularity approximately 20 billion years from now. Young-Wook Lee at Yonsei University in South Korea and colleagues analysing supernova expansion data published in 2025 found independent evidence consistent with a universe already entering a phase of decelerated expansion, supporting the crunch scenario on empirical rather than purely theoretical grounds. None of these three endings can currently be eliminated by the available data. The dark energy equation of state measurements from the dark energy spectroscopic instrument and from supernova surveys do not pin down WBE precisely enough to determine which side of -1 the universe currently occupies, or whether it has crossed from one side to the other. The question of whether the cosmological constant is truly constant or is evolving is what the surveys were designed to answer, and after the most precise large-scale structure measurement ever conducted, the answer remains genuinely ambiguous between scenarios leading to three completely different futures. The James Webb Space Telescope confirmed that measurement error is not responsible for the cosmological tensions. Better data has made the ambiguity more precise without resolving it. What is particularly striking about the current state of the field is that 25 years ago, the question of the universe's fate appeared settled. The discovery of accelerating expansion in 1998 ruled out the Big Crunch, to most researchers' satisfaction. A universe expanding forever, driven by a cosmological constant, would proceed to the Big Freeze, cold, dark, and infinite in duration. The Big Rip was acknowledged as a theoretical possibility, but required a phantom equation of state that seemed unlikely in the absence of evidence for it. 2.5 decades of precision measurement, culminating in the James Webb Space Telescope's confirmation of the Hubble tension and the dark energy spectroscopic instrument's evidence for dark energy evolution, have dismantled that apparent settlement. The Big Crunch has been revived by Tye's analysis. The Big Rip has been made more plausible by evidence that the universe passed through a phantom phase. The Big Freeze remains possible, but now depends on dark energy remaining stable in a way that the measurements no longer confirm. All three endpoints sit before cosmology with roughly equal scientific standing, separated from one another not by which model has more data supporting it, but by which interpretation of the same ambiguous data each one requires. The timeline of the Big Crunch scenario in Tye's model is specifically worth holding against familiar reference points. The universe is currently 13.8 billion years old. The contraction phase would begin approximately 11 billion years from now, when the effective cosmological constant has evolved enough that gravity's pull on the larger scales overcomes dark energy's push. At that point, the Andromeda and Milky Way galaxies will have long since merged into the single elliptical remnant called Milomeda. The first effects of the reversal would be subtle, a deceleration of the expansion too small to detect against the noise of local gravitational motions. Over the following hundreds of millions of years, the deceleration deepens. Galaxies that have been drifting apart for more than 20 billion years stop and begin, slowly, to approach one another. The cosmic microwave background, stretched by decades of additional expansion, begins gradually warming as the contraction compresses the volume of space. In the final stages, the compression accelerates, temperatures rise, structures dissolve, and the universe returns to a state resembling its earliest moments, before reaching the singularity approximately 20 billion years from now. Whether a new expansion follows, whether the singularity produces another Big Bang and another universe, is beyond what current physics can predict. What the telescope confirmed that we did not want confirmed. The James Webb Space Telescope began science operations in the summer of 2022. By early 2026, roughly 3.5 years into its primary mission, it had returned results that required revisions to the standard model of galaxy formation, confirmed a fundamental crisis in the measurement of the universe's expansion rate, detected chemical enrichment in the most distant confirmed galaxy that demanded multiple stellar generations to have lived and died before the first model's predicted star formation had properly begun, and catalogued a population of black holes so massive and so early that no accepted physical mechanism could assemble them in the available time. It had shown galaxy mergers at 800 million years producing stars at 100 times the Milky Way's current rate. It had confirmed that the structure of the cosmic web at both early and late times exceeds what the standard model's simulations produce, and it had been applied to the most contested measurement in cosmology, the Hubble tension, and found that the tension is not instrumental. It is real. The specific character of what the telescope confirmed matters. It did not reveal that the universe is large. The scale of the universe was established by Hubble's observations in the 1920s and has been refined continuously since. The distance to the nearest large galaxy cluster, to the edge of the observable universe, to the cosmic microwave background, these numbers have been in textbooks for decades. Familiarity with large numbers is not the same as confronting a framework failing under precise measurement. What the telescope confirmed is that the framework used to understand the universe, a framework that had passed every observational test put to it for 40 years, is systematically wrong about what the early universe did, and that the wrongness is not a minor calibration issue, but a category-level discrepancy between prediction and observation. The Hubble tension, confirmed to be real by the most capable photometric instrument ever deployed, places two of the most precise measurements in the history of science in direct and unresolved conflict. One measures the expansion rate by reading the universe's initial conditions. The other measures it by reading the universe's current state. They disagree at 5 sigma. There is no version of the standard model in which both measurements are simultaneously correct. Either the physics describing the early universe is incomplete, or the physics describing the local universe is incomplete, or there is new physics connecting them that has not yet been identified. All three possibilities require changes to the framework. The telescope did not point toward which change is needed. It confirmed that a change is needed definitively, at a precision that cannot be attributed to measurement uncertainty. Dark energy, the dominant component of the universe, may be changing over time. The Dark Energy Spectroscopic Instrument's 2024 results found evidence for this at 3.9 sigma, significant enough that it cannot be dismissed as statistical noise. If dark energy is dynamic rather than constant, then every prediction about the universe's fate that depended on the cosmological constant's constancy requires revision. Whether the universe ends in cold dispersal, violent dismemberment, or gravitational collapse is again genuinely uncertain, for the first time since 1998, when the accelerating expansion appeared to settle the question in favour of eternal expansion. What the telescope did not do, and what has perhaps generated the specific anxiety visible in the astronomical community's response to its results, is provide a clear direction for revision. When an anomalous result appears and points toward a specific missing ingredient, the path forward is identifiable. When anomalous results appear across multiple independent measurements, all pointing toward inconsistency with the standard model but not consistently toward any single alternative, the situation is harder to navigate. The early galaxy surplus could be addressed by modifying dark matter models, or by revising star formation physics, or by changing the initial conditions from inflation. The Hubble tension could reflect new early universe physics, local void effects, or systematic errors in the distance ladder that the telescope failed to find. The dark energy evolution could indicate quintessence fields, modified gravity, or interactions between dark energy and dark matter. Each anomaly has a menu of potential explanations, and the menus do not consistently overlap. A single new physical ingredient that simultaneously resolves the early galaxy problem, the Hubble tension, the little red dots, and the dark energy evolution has not been proposed, let alone confirmed. This is the position the field occupies as of 2026. The universe has been shown to be stranger than the best available model describes at multiple independent levels by the best available instrument. The instrument will continue operating, accumulating data, and sharpening the constraints. What it is most likely to do is make the discrepancies more precise, which is valuable. But precision in the measurement of an anomaly is not the same as an explanation for it. The explanation will require theoretical work that is currently in early stages, being driven by data that no previous generation of cosmologists had access to. The history of physics provides context for how these crises resolve, though not comfort about the timeline. Newtonian mechanics described planetary motion with extraordinary precision for 2 centuries before the precession of Mercury's perihelion provided a discrepancy that classical physics could not explain. The resolution came in 1915 with general relativity, not a small correction to Newtonian mechanics, but a fundamentally different description of gravity, space, and time, from which Newtonian mechanics emerges as an approximation valid in the limit of weak fields and slow velocities. The anomaly pointed towards something genuinely new, rather than a fixable error in the existing framework. General relativity was not proposed because physicists suspected it was needed. It emerged from Einstein's theoretical investigations into the foundations of mechanics, motivated partly by the Mercury anomaly, but not derived from it by any simple process. The new framework, when it arrived, resolved not just the Mercury problem, but provided a language for describing phenomena that Newtonian physics had no category for. The current crisis in cosmology has some structural similarities. The James Webb Space Telescope's anomalies are not pointing toward a small numerical correction to the standard model. The early galaxy surplus cannot be resolved by adjusting the star formation efficiency parameter by a few percent. The Hubble tension cannot be resolved by a small recalibration of the distance ladder. The little red dot black hole masses cannot be explained by a modest extension of accretion physics. Each anomaly requires something categorically new, either new physics in the dark sector, or new physics in inflation, or new physics in the way gravity operates at early times and large scales. Whether the new physics required is a single coherent framework that addresses all the anomalies simultaneously, or a set of independent additions, each addressing one problem, is unknown. What is clear is that the telescope has provided the data that will drive whatever revision comes next, and that the revision will not be small. The scientists operating the telescope, analysing its data, and publishing the results that have produced this situation are not in a state of professional crisis in the sense of uncertainty about whether they have done something wrong. The opposite is closer to the truth. The telescope is working correctly. The calibrations are sound. The results have been cross-checked by independent teams using independent methods, and they agree. The crisis is not in the instrument or the measurements. It is in the theory, and a theoretical crisis driven by correct, precise measurements from the best instrument ever built is exactly what productive science looks like from the inside during the period before the resolution arrives. The cosmological crisis triggered. The James Webb Space Telescope did not show us that the universe is terrifying because of how large it is. Every number in this script has been large. The distances, the masses, the timescales, the temperatures, all of them exceed anything that intuition built from human experience can absorb as more than abstraction. The size of the universe has been known, in approximate terms, for a century. Hubble's measurements in 1929 has been absorbed, processed, and filed in the category of large numbers that are acknowledged without being felt. What the telescope added was something more specific and more disorienting than scale. It showed that the framework built to describe this large universe, refined over 4 decades by thousands of researchers using the most precise instruments available, is wrong about what the universe did in its earliest and most consequential chapter. Not slightly wrong, not wrong at the edges, but wrong at the center, about the processes that determined everything that came after. We exist in the only window in cosmic history during which the universe's full past is readable. The cosmic microwave background is still detectable. The most ancient galaxies are still visible. The chemical history of the first stars is encoded in spectra that instruments can still receive. This window is open now, and it is only now that an instrument has finally been deployed with the sensitivity to read what it contains. What that reading returned was not confirmation that the model was correct and the universe behaved as expected. It returned a systematic pattern of discrepancy, consistent across independent programs, independent teams, and independent wavelength ranges, pointing toward a cosmos that assembled itself faster, more efficiently, and more chaotically than any simulation built on the standard parameters has produced. The early universe was not the quiet, gradual awakening the textbooks described. It was something the field does not yet have an adequate framework to fully characterize. The telescope continues operating. Each new observing cycle adds depth to the catalogue of early galaxies, precision to the Hubble constant measurements, detail to the large-scale structure maps, and constraint to the dark energy equation of state. The instrument is doing exactly what it was designed to do, reading the universe at wavelengths and sensitivities previously inaccessible, returning data that existing frameworks must be tested against. What those tests have so far revealed is that the frameworks need revising at a fundamental level, and that the revision has not yet arrived. The universe is not waiting for it.